Hello. Can you see my screen?
Yes, sir. Screen is visible, sir.
Actually, my video is also on, but I don't see myself.
So your video also visible, sir, at the right side top corner.
So should I start?
Sure, sir. It's almost 6:45. Yeah.
Yeah. So anyway, I'm going to recall.
Okay, sir.
So yeah. Good evening, everyone. So we started talking about continued fraction last time. So we had seen some kind of pictorial motivations to do it, and saw two examples. So we won't I won't repeat those things, but let me just repeat the theory that we started, so that we need to develop for the next two lectures. So just to have our notations right, so we haven't made much of an assumption on AN yet. So just assuming that ANs are non-zero except possibly for A0. We are going to make assumptions a little later. So this is like just doing like algebra. So where you can consider them as variables. So doing it in that way has a bit of advantage because you can consider the kind of thing I'm doing here. So if you have a continued fraction of length capital N, then I write it as a fraction up to n minus 1 and then put all the things together as a single entry. So if we are assuming that all of them are real, all of them are integer, then we can't do that. That's not a. That's the last one is not an integer. But if we are treating it in just in algebraic way, then it's fine. So they are just real entries. Okay. So to our notations were these PNs and QNs. So PNs or QNs are defined recursively via these relations, these past two lines. And also we have shown that, so that was the first proposition that we proved, that a continued fraction A naught A1 to AN can be written as a quotient QPN by QN. So QN being the denominator, PN is the numerator. So, and we are going to call these the nth convergence, this quotient Pn by Qn, which is also equal to this. So these are going to be called nth convergence. And these entries are known as partial quotients. So ANs are partial quotients. Yeah, so this is, yeah. So ANs are partial quotient. Yes, so that's what is written there. ANs are partial quotient. And the tail part, so a small n to a capital N, that's called the nth complete quotient. Okay, so that was the first thing we proved. We proved some little bit more. The second important equality was this, that Pn Q into Qn minus 1 minus Pn minus 1 Qn is minus 1 to the n minus 1. And we also have proved the similar thing for a gap of 2. So yeah, this is what it is. This one, yeah, the equation 3. So that's a similar thing where you are jumping from n to n minus 2. So let's start from, yeah, so these are the relations we are going to require. That's why we numbered them. Let me start with these things. So now it's time to have assumptions. So we of course need some assumptions. the conventions. So let me just write it in a different. Conventions. So, so all these ANs are going to be assumed to be positive, non-zero positive. A naught, of course, can be zero. It also can be negative. So A naught can be 0 or negative. And most of the time we are going to work with integers. ANs is all integers. So that's what I'm saying, that if so henceforth that will be our standard assumption unless we say something else for some results. So ANs are integers. So they are natural numbers, as they are all non-zero, positive. So ANs are integers, and we are going to call this continuous. Then the continued fraction is. Then we call it a simple continued fraction. Simple fraction. So just for a bit of convenience, we would also denote this. So let Xn is the convergence, the nth convergence, which is Pn by Qn. And we have shown this equality as well. So this is up to An. So this is defined to be Xn. And so we would just write this, that we recall these two things that we have already shown, that Pn by Qn minus Pn minus 1 by Qn minus 1 is going to be minus 1 power n minus 1 no, we don't really need this. I need the other one. So n minus 2, this is equal to so minus 1 to the n minus 1, no, minus 1 to the n, An by Qn minus 2. Therefore, with the above notation, this is Xn minus Xn minus 2 into minus 1 to the n by whatever we already have, Qn. So Qn minus 2. Now with our assumption, this ANs and QNs are all positive, all non-zero positive. Therefore, if n is even, then minus one to the n is positive. It's just one. So right hand side is positive. Let me just write it. So right hand side is positive. So we can make this observation that if so that is important. So if n is even, then right hand side is positive. Therefore, xn is strictly greater than, so it's not zero as well. So I'm assuming all these ans to be positive, non-zero positive numbers. So xn is greater than xn minus 2. And n is even, so all these even convergence increase strictly. So that is to say that even convergence increase strictly. So they are going to strictly increase. And similarly, if n is odd, then the right hand side is going to be negative. Therefore, the odd convergence are going to decrease strictly. Similarly, the odd convergence decrease strictly. So these are the two things we can immediately conclude. One more thing we can easily conclude is the following, that okay, let's just write it as a proposition. So all these small propositions are going to be useful and important. They are all very easy to prove. So most of them I'm going to prove, and some of them I would include in my notes, but not prove it in the lecture. Every odd convergent is greater than every even convergent. Greater than any even convergent. So proof of this is quite simple actually. So so if not, let me just give a quick proof. So if not, so suppose not, and so this is saying that every odd convergence is greater than any even convergent. So suppose at some place it is the other way around, that and x say to a 2m plus 1 is, so that's an odd one, it is less than equal to some other x2k, say, that an odd one is less than for some m and k. So if now the point is, so we need to compare this m and k. So if m is less than k, then what we get is this thing. So if then what you have is x. So this is so if I look at this odd convergent and k is bigger, so x2k plus 1 is going to be strictly smaller than x2m plus 1, and this is x2k. Okay. But so let's have this, and if f is if it is the other way around, so if k is say greater than equal to m, then x2m plus 1 is greater than equal to x2k and x2m, because odd convergence are increasing and even convergence are decreasing. Odd convergence are increasing and even convergence are decreasing. One second. There, that one. Yeah, even convergence are increasing. So this is, yeah, this is correct. So in both cases, we get this thing that x2k plus 1 is less than equal to x2k. And here as well, we have x2m is, in both cases, actually it is strict because we have equality here, but not in the other. But this is a contradiction. So why is this a contradiction? Because of the first relation that we have. This is what we have last time from this two. So Pn, let me write that. So just recall this, that Pn by Qn minus Pn minus 1 by Qn minus 1 is minus 1 to the n minus 1 and by Qn minus 1 Qn. So that is in our notation xn minus 1 is minus 1 to the n minus 1 and Qn minus 1 Qn. So what can we conclude from here? So if n is even, then even, say n is even, say n equal to 2m, then x2m minus x2m minus 1 is equal to is minus 1 to the 2m minus 1. Right? This is minus 1 to the something odd. So that is negative. So this is less than. Therefore, x2m to m minus 1 and if n is odd, then the other thing happens. So say x n is 2m plus, or change it something, so 2k plus 1, then x 2k plus 1 minus x2k is positive because it's n minus 1, so this just changes the parity. So if you have odd, then you would have positive, and if you have even, then it's going to be negative. So yeah, so therefore x2k plus 1 is greater than x2k, and this happens for every k, and similarly the previous one, and that's a contradiction because that is what is being reversed here. So it's 2k plus 1 is less than equal to strictly less than, in fact, x2k, and just a similar situation here as well. So that's not possible. Yeah, in fact, what we need is just the last one, not so this one, the even case we really did not need. So only the last one is enough. So this is enough to get the contradiction. This holds for all. Yeah. So this contradiction tells us that this kind of thing doesn't happen, and every even convergence is greater than. Every odd convergent is greater than any even convergent. So, so what is the picture? So the picture is going to be like this, that of course we would see the full thing a little later. So if you have, let me just draw a line. So, yeah. So if you have this, so suppose this is the number of which you have written this. This is this full number. So this will always be the notation for the continued fraction we are considering. And now odd convergents are all bigger than the number. Odd convergents are all bigger than the number, and they are decreasing. So odds are on this side. So odd convergence. Let me just write odd convergence. Sorry? No, this is not a question. So yeah, so odd convergence are decreasing. So they are all bigger than all the even convergence, and they are decaying, strictly decaying, in fact. And even convergence are all smaller than them. So they are on this side. And they are increasing. So we would have a more clearer picture, and in a quantitative sense a little later. So let's go ahead.
So you can use the nested interval theorem. You can find the intervals. You can use the nested interval.
Yeah. So so that kind of thing we are going to do. I mean, we would see the rate of convergence. Yeah. So some of the things I'm going to skip actually. Okay, so some simple properties. So some of them I would just mention without proof. So some properties of so we would be dealing with simple continued fractions. So in entries are all integers. One. So Qn. So yeah. So okay, let me also mention what do I mean. So just to recall that an is greater than 0 for all n greater than equal to 1 with the exception of n equal to 0, and an's are all integers. So an's are actually greater than equal to 1. So the first property is Qn, the denominator of the convergent. So they increase. So that happens for all n greater than equal to 1. So all n greater than equal to 1. And strict inequality, if you are looking at an n which is greater than equal to strict inequality, for all n greater than equal to 2. So if you just leave 1, then you have strict inequality. Second one is essentially a consequence of this. So this is greater than equal to n. Qn is greater than equal to n for all n greater than equal to 1. And again, strict inequality for a greater than equal to 3 in this case. 3. And there is a third property. Just let me list all of them and then we'll discuss a quick proof. So the third property is the following, that the convergence are always in their lowest term. So Qn, Pn and Qn. So GCD of this. So say GCD of Pn, Qn. This is always going to be 1. So these fractions, the rational numbers Pn by Qn is always in their lowest form. Yeah. Let's see this. So I just say so sort of a sketch of the proof. So first one, actually this all of them follows from just the definition. So let's just, so Q naught is 0. Q1 is A1, which is greater than equal to 1. And because the ANs are all assumed to be non-negative, and they are integers, so they have to be greater than equal to 1, all of them. So, and the Qn is defined recursively as an Qn minus 1 plus Qn minus 2, and therefore it is bigger than Qn minus 1, strictly larger than this. As yeah, so in fact, the last one is bigger than 1, so I have an 1 in fact. So for all n greater than equal. So that we prove it just by induction. And this thing, yes, and the second one is also similar. So second one also follows from definition. So this follows similarly, so just from the third one is very easy from the formula that we have proved. So Pn Qn minus 1 minus Pn minus 1 Qn. So this is minus 1 to the n minus 1. And therefore, Pn and Qn cannot have a common divisor other than 1. So if D divides Pn and Qn both, so if D divides Pn and D divides as well Qn as well, then D divides minus 1 to the n minus 1, because it's going to divide the left hand side, therefore it divides the right hand side, which is just minus plus minus 1. Therefore, D has to be 1. So GCD has to be 1. Yeah, so what we need to now talk about is uniqueness of continued fraction expansion. So an example to illustrate the situation. Let's write down. So we would discuss uniqueness now. Uniqueness of continued fraction expansion. So let's start with an example, just a small example. So suppose we consider the continued fraction 2, 2, say 3. So how does it look like? So this is 2 plus 1 by 2 plus 1 by 3. This is what the continued fraction is. Now I can just manipulate it in this way, that 2 by 2 plus 1 by 2 plus 1 by 1. I can write it like this. Because 1 is allowed in the entry. So if I write like this, then this same number is also 2, 2, 2, 1. And I can always do this. I can always for anything. I mean, this first entries doesn't matter. Whatever be the last entry, if it is more than 2 or more, then I can just split it up into into say if the last entry is A, and then I can always so yeah, in general. So what what I can do, if I have this continued fraction an, and so I can write it as a naught a n minus 1 till previous entry. I don't do anything. Then I write a n minus 1, just one less, and then put in 1. I can do that. Of course, if this can be done only if an is at least 2. So if it is at least 2, I can always do this trick. So that will violate uniqueness of the expansion. But we are going to show that except for this situation, the expansion is unique. So this is a situation where it is of course not unique, and we cannot rule it out a priori. So we'll show that except for this, it is unique. So if you have last entry, if you insist that the last entry is at least 2, then it is unique. Let's go ahead with the proof of that. Okay, to do this, what we need to prove is the following. So let's we have so let x be equal to an, and an so this we already have defined. So for 0 less than equal to n less than equal to capital N, an dash. So what we call this complete quotient. So I just write that again. We require this. So this is what is complete quotient. So as you can see that x is a naught dash, because if you take the complete quotient of the first complete quotient, then you get the full continued fraction. It is x. And we also have this relation. Okay, for n equal to 1, yeah, x is this, and x is also, you can write it as a naught a1 dash, a naught a1 dash. So this is a naught plus 1 over a1 dash. Therefore, I can write it as a naught a1 dash plus 1 by a1 dash. So the same number I'm writing in this way. And in general, so these are the case for n equal to 0 and n equal to 1. So n greater than equal to, for n greater than equal to 2, I can write it as a n dash q, sorry, pn minus 1 plus pn minus 2 this is with the dash. So this is a n dash q, okay, sorry, this is qn minus 1 plus qn minus 2. This actually we have seen earlier. So this is for n greater than equal to. So for n greater than equal to 2, you can write it all the way up to capital. Now, what we need to prove is the following. Let's call it a theorem. An is the integer part of, okay, so there is a slight abuse of notation. So this, the notation here is not of continued fraction, but this is the integer part. So this is the greatest integer less than equal to an. So what is generally called the integer part? An dash. So if you take the integer part of the complete quotient, innate complete quotient, you get an, the partial quotient, innate partial quotient. So we need to prove that. Yeah. So in fact, this has a lot of bearing on the uniqueness proof, and this also has a change if we are looking at capital A. So except, so there is an exception. So this equality holds. This equality holds except in this case, except when an equal to 1. Except when an is equal to 1. Whenever the last entry is 1, and in that case, okay. Let me just move this. And in that case, an is equal to an minus 1 dash minus 1. So this happens if okay, sorry, n minus 1. An is of course 1, so there is nothing to say about it. So an minus 1, the previous one, does not satisfy the general form. But it is less by 1. So that we can see here that it has just shifted. We have shifted 1 to the last entry. So that's the reason it has become an minus 1. So that reflects here. Okay. So let's prove this. So proof. So clear if, okay, let's say it obvious. If capital N is equal to 0. So the continued fraction has only one entry. So that's just an integer. So that's just the A0. And in that case, A0 is going to be equal to the complement. So A0 is going to be equal to A0 dash, which is going to be an integer. It's just one entry. It's just an integer. So that's obvious if n is 0. So suppose n is not 0, so n is at least 1. So n is at least 1. Then, so if you then for say 0 less than equal to n less than equal to n minus 1, an dash is equal to an plus 1 over an plus 1 dash. So that's obvious, right? Because an dash is just this an to the end an. Therefore, this you can just write it. If you take an out, then you can write it as this, that an plus 1 to an. So which is this? The n plus 1 at complete. So this is what we have. Now, if an plus 1 dash is equal to 1, so if it is equal to 1, then this has to be the last entry. You can't proceed anymore. So this has to be the last entry. So n plus 1 should be equal to n, and an is also 1. So if that's not the case, so if an plus 1 dash is greater than 1, so these are the cases we are interested in. So this is the exceptional case. So this first case, this is the exceptional case, and that we mentioned in the beginning, and this is the case we are more interested in when an plus 1 is greater than 1. So if an plus 1 is greater than 1, then let's go back to the relation we have. So this relation, so I mean this relation. And what does it give? So this one. So an dash is an plus 1 over something which is bigger than 1. So 1 over an plus 1 dash, this part is less than 1. So an is an dash. Of course, an dash is bigger than an, but it's also smaller than an plus 1. And therefore, we have what we wanted, that an dash, so this is the integral part, is going to be exactly an. Because this entry an dash is between an and an plus 1. So therefore an, and an is an integer, so it is the integral part. Yeah, so this one is going to hold for 0 less than n 0 less than equal to n less than equal to n plus 1. And for last entry, it is obvious. And for the last entry, it is an is going to be an dash, because there is nothing remaining, and which is also the an dash. It's just an integer. So okay. So now we are ready to. So this is the theorem we would require to establish the uniqueness, except in the exceptional case we mentioned. And so let's just remember that. So it's essentially for every n, an is the integral part of the complete quotient. Let me state the uniqueness theorem. Let's state it as a theorem again. So this is what is uniqueness in this case. So if two continued fractions a naught, a1, a say n is equal to some other fraction of say some different length. If these two are equal, then and with that assumption, so we want to exclude that possibility that we have seen in an example, that you can always extend the length by 1 by putting a 1 at the end and reducing 1 from the previous entry. That you can always do. So this, if you assume that the last entry is larger than 1, so it's greater than equal to 2, in that case, so that's the case we are considering, we can show uniqueness in that. So if this is the situation, that two continued fraction expansions are the same and last entries are at least 2, last entries of both are at least 2, then they are same. So that's what. So then m is going to be equal to m. So they are first of all of the same length, and the fractions are identical, and the fractions are identical. So by identical, I mean all the partial quotients are equal, are identical. So I mean that all these are equal. So all, okay, let's just write it in language. All partial quotients, so all the entries, quotients, all partial quotients are equal. Yeah, so let's prove that. So proof is by induction. Okay. Let's write down a complete proof. So proof is by induction. So we use induction. induction on n. Sorry. Okay. So we use the last theorem all the time. So just use the last theorem. So what does it say? It says that A naught dash is equal to A naught, and so the integral part of complete quotient is partial quotients. So integral part of nth complete quotient is the nth partial quotient. So an is the integral part of an dash. So you use it for 0. And similarly, because similarly for this other expansion, B naught dash is also going to give us B naught. So this is by the last theorem. So this is by last theorem. But now observe that these continued fractions, the expansions we wrote down in the beginning is the same as this A naught dash. So that's the number. So A naught dash is actually this whole thing. Which is same as the other one. That's the assumption. And this is B naught dash. The 0th complete quotient is the fraction itself. So therefore A naught have to be equal to B naught. And suppose sorry. So suppose we have shown that A naught is equal to B naught and so this is our induction hypothesis. Then A minus equal to B minus. So suppose we have shown this. So what we want to show is An equal to Bn. So therefore what we have is actually it would have been better to write this number as x so that I don't have to write. So let's write it as x as we were doing earlier. So let's call this number x. Otherwise recalling the number becomes difficult. So we have these two expressions for x, two continued fraction expansion, so to say, two continued fraction expansion for x, and by induction hypothesis we have first n entries to be same. First n plus 1 entry. Yeah, n entry. I went up to 0 from 0 to n minus 1. So n entries. So 0th entry we have shown, and then this is suppose this is happened. This happens up to n minus. So for n at least 1. Then x is written as A naught to A n minus 1 A n, and the last entry is A capital. And this is same as, So we have shown that the first entries are all equal, and then we have Bn and so on. It goes up to the same. So what we need to show is that this is so if we use the notation of complete, okay, let's write this. Should I write? Yeah, I think it's better to write in this line itself. So yeah, I also want to write it as a naught to a n minus 1, and then this is a n dash. And this is b naught to bn minus 1 and bn dash. So lengths of an and an dash and bn dash are different. Apparently, we haven't proved anything. Okay. So there is a small point actually. The thing is, I would require the induction hypothesis for greater than equal to 2. So we should also prove the case. So here we are getting only greater than equal to 1 because I have only proved the 0th case. So let's prove the case 1 as well, A1 directly. Let me prove that. So for n equal to 1, let's prove this case as well. So this number x is equal to a naught plus 1 over a1 dash complete quotient. This is equal to b naught plus 1 over b1 dash. And we have already shown that a naught is equal to b naught. So a naught is equal to b naught. Therefore, a1 dash, this is a1 dash, the first complete quotient, quotients are equal, b1 dash, this is equal, and therefore their integral parts are also equal. Okay, let's write it like this. So a1 is nothing but the integral part of a1 dash. This is again the previous theorem. And an dash is equal to a1 dash is equal to b1 dash. Therefore, their integral parts are equal. And therefore, this is equal to b1 again by the last theorem. So this first and last equality uses the last theorem, and equality of a1 dash and b1 dash implies that their integral parts are also equal. So we have the result for n equal to 0 and n equal to 1. Therefore, here we can make this assumption for n greater than equal to 2. Oh, something just happened. Oh, is it my internet connection? Am I audible and visible?
Yes, sir.
Audible,
Yes.
sir.
Okay.
Okay.
No, I just saw a notification, so I thought there's something wrong. Some maybe something else.
Okay, sir.
Yeah. So we have shown this equality of partial quotients for the n equal to 0 and n equal to 1. Therefore, we can make this induction hypothesis for n greater than equal to 2. So that is required because we want to now write x in the square. So what we have already seen. So this is an dash pn minus 1 plus sorry, this is pn minus 2 and
The denominator is qn.
q. Yes, thank you. Qn. Denominators are all and this is also equal to bn dash pn minus 1. So this is where I'm using the induction hypothesis that up to n minus 1, all these entries are same. So a naught is equal to b naught, a1 is equal to b naught, and so on till a n minus 1 is equal to b n minus 1. So therefore, all this convergence are exactly the same. So up to n minus 1. So pn minus 1 is same for both these numbers. So pn minus 1, but we don't know whether pn is same for both the number or qn is the same for both the number. That we don't know. But till n minus 1 we know. So that is where the recursion formula comes really handy. So this is also bn dash qn minus 1 plus qn minus 2. And let's just multiply this out. So an dash bn dash, just cross multiplying this. So pn minus 1 qn minus 1 plus an dash pn minus 1 qn minus 2. Yeah, so multiplying by q. Okay, I should just do it from one side. So this I multiply. Okay, let's do it like this. So I'm multiplying by this first thing. So bn dash pn minus 2 qn minus 1 then multiply by the second entry in this denominator. So an dash pn minus 1 qn minus 2 and plus, okay, let's write it, plus pn minus 2 qn minus 2. Okay, done with that side. Then here again, the first entry is an dash bn dash pn minus 1. So this is going to cancel actually. Then let's multiply in very similar way. So an dash pn minus 2 qn minus 1. That's multiplying by the first thing, and then we have the second thing. So bn dash pn minus 1 qn minus 2 plus Pn minus 2 Qn minus 2. Yeah. So the first and last entry cancels. First and last entry cancels. So what remains as these coefficients an and bn. So we keep it in different sides. So an dash, let's keep it on this side. So Pn minus 1, Qn minus 2 minus from the other entry Pn minus 2, Qn minus 1. So this is equal to Bn dash. Let's keep Bn dash on that side. So that is again the same. So Pn minus 1, Qn minus 2 minus, let's see if we have done the multiplication correctly. Should be the same. Yeah. And now An dash and Bn dash are equal if the bracketed expression is not 0, and we know that it's not 0. It is so since it is minus 1 to the in right, yeah, minus 1 to the p to the n minus 1 Qn minus 2 minus Pn minus 2 minus 1 to the n, or even n minus 2. Actually, if we just write according to that formula, we have to write n minus 2. So n minus 2 and n are same. They are the same. And therefore, An dash is equal to Bn dash. And induction proceeds in that way. Yeah. So then what we prove so far? Oh yeah, it is not over. So if they are equal, then again we use the previous theorem to show that An and Bn are equal. That is fine. So this is the integral part of An and integral part of Bn. And this is Bn. So therefore An is equal to Bn. That's what we wanted to do. Now suppose make an assumption about n and m. So suppose, so we are going to prove these equalities till we reach the end of one of these numbers. So suppose an is smaller. Suppose n is smaller. So we exhaust all ans and then we are still left with, we might be left with some bn. That possibility is there. So suppose, because we don't know a priori that capital N is equal to capital N. So we have to make an. So let's do this. The other case would also be exactly the same, just replacing a by b. So suppose n is less than equal to m. So if they are equal, then it's fine. That's what we wanted to prove. So okay, let's see that. If they are equal, of course there is none. That's what we want. So we say that n is strictly less than m, and then arrive at a contradiction. So that will show that they are. So if that's the case, we already know. So by the above induction that we have done so far is An is going to be equal to Bn for all n less than equal to capital. So up to n we have exhausted all of them. So all of them are just same, the partial quotients. Now the number x is equal to P capital N by Q capital N. And how does this number look? So this is AN. We know these entries are same. So up to this capital N, the entries are same. Then we have Bn plus 1. It might have some extra entry. It is going to have some extra entry because M is bigger than N. So at least this much. So it goes up to M. M can as well be N plus 1, but strictly bigger than capital. That's the assumption. We want to get a contradiction. We want to say that that doesn't. So what is this quantity? We can write it as A naught to AN, and then Bn plus 1 dash, the complete quotient. So this is the same as the complete quotient. And this is written as now Bn plus 1 dash so this can be written as Pn plus Qpn minus 1 Qn. So just one less and then two less. So this is the formula we are always using. So we can write it like this. And because we have proved these things are equal up to the partial quotients are equal up to capital N, up to the nth stage, and therefore all these Pn's and Qn's are equal up to that stage. So we can write this. The last one below. And now let's cross multiply. So this is the same. This is same as Pn by Qn. Yeah. So why is this? Why is this equal to Pn by Qn? Because this is. Let me actually write it like this, and it will be very clear. So let me write it like this. So. So this is Pn by Qn. This is the entry. So that's what we started with. We have this expression, and also we have this expression. They are equal. That's what we started with, and then if it has some extra length, so that's what we are trying to say that it cannot. So now we can cross multiply with this. We can just cross multiply with this Pn by Qn. So by doing that, let's do that. So this is Bn plus 1 dash Pn, P capital N, Q capital N. So multiplying this by Pn. So Pn, P capital N, Qn minus 1 is equal to Bn plus 1 dash Pn Qn plus Pn minus 1 Qn. So the first entry cancels, both are same. What remains is Pn yeah. Yeah, and this cannot happen. This is a contradiction. as this thing, as we know actually that Pn Qn minus 1 minus Pn minus 1 Qn is minus 1 to the n minus 1. Minus 1. So whatever, I mean, it is non-zero. So this is a contradiction, and it shows that what led to contradiction is this assumption that n is strictly less than m. That's not possible. So therefore, n and m are exactly equal. So n is equal to m, and we have already proved the equality of the complete of the partial quotients. So what we have to do now is to look at the algorithm to compute continued fractions. Okay, so I think the time is essentially up. So I would stop today. Next day we would approximate. Yeah, we need to do this algorithm. That won't take much time. So yeah, next day we can start looking at the approximation by continued fractions. And, yeah.
Okay, sir.
Yeah. So you can actually try to compute some examples. So I'll be sending whatever I'm writing as I sent last time. So you can try to just compute some examples. And by the method what I have already done in the first class. It'd be nice to look at some examples. Okay. So stop share.
Okay, sir. Thank you so much, sir.
Okay. Thank you. Thank you.
Okay, sir. We will meet again coming Thursday.
Yeah.
Thank you, sir.
Thank you. Thank you for attending. Thanks everyone for attending.
Thank you, sir.